Let's continue looking at our example of Jacobi with one-sided communication to do the ghost cell exchange. Now, as we mentioned, we assume that we have global pointers that reference the memory corresponding to our neighbors' grids. And this is what actually allows us to do one-sided communication. A global pointer references memory that lives inside the shared segment, and that is what we are permitted to do one-sided communication on. The next step is to discuss how to actually get memory allocated inside the shared segment. Now, the standard C++ new operator allocates inside the private segment. To allocate inside the shared segment, we need to use UP++ allocation operations instead. For allocating just a single object, there's a new underscore function template to do that. In our case, though, we want to actually allocate an array of elements, and so we have a corresponding new underscore array function template that does that. We give it the element type as a template argument, and then as the function argument, we give it the number of elements. And so it does the allocation inside the shared segment and returns to us a global pointer referencing the start of that memory. These allocations are not collective calls. Each process does its own allocation independently. There's no synchronization. So if we were to proceed after this allocation to use something like RPC to retrieve these pointers, then we would need to introduce our own synchronization to make sure that the allocations have completed. So the reason why these aren't collective is because UP++ doesn't maintain a symmetric heap. And instead, the pointers need to be communicated explicitly before other processes can access the data. We'll talk in a little bit more detail as to why we don't maintain a symmetric heap, but briefly speaking, a symmetric heap requires non-scalable data structures, and it also doesn't compose well with subset teams. So we get a global pointer back from the allocation. For our local computation, we don't actually want to be using the global pointer for that directly. First of all, the syntax for accessing the underlying memory is using an rput or an rget. And again, our reasoning for that is that we don't want syntax to be hiding communication. So rput and rget make it explicitly clear that this is doing communication. For something that lives in memory that we can directly address, what we want to do instead is convert it to a local pointer and then use the standard C++ dereference operator to access that memory. So we refer to this as downcasting. We downcast a global pointer down to a local pointer, and the way that we do that is with the local member function on a global pointer. And this is only valid if the calling process actually has load store access to the underlying memory. So as an example, again, here we have our two global pointers that we just allocated memory for. And we also have local pointers to refer to the same memory locations, but with the local pointer abstraction as opposed to the global pointer. And so if we look at our allocation function down here now, we called new array as before to obtain the global pointers. To obtain the corresponding raw C++ pointers, we call local on the result. And that gives us back just a standard C++ pointer. This only works when we have load store access to the underlying memory, but since we're the ones who allocated the memory, we know that we have that. We'll also see later that we can actually do this with global pointers from processes that share physical memory with us. One last thing I want to mention is that because we're using global variables to store our pointers, we can actually access them using an RPC. However, we'll actually set up our communication using something different. So let's look at the details of an actual iteration. So setting aside the setup part of it. In this example here, we're actually now doing the overlap rather than doing the wait directly on the result of an rget. We start off our iteration by launching our gets to our two neighbors, and again giving the corresponding local and remote pointers, with the source being a global pointer and the destination being a local pointer. Here we're actually using the vector versions, so we have to give it an element count, and also we get a feature that just represents completion of the operation rather than containing the result itself. Okay, and what we're actually doing is we're storing the value that we're obtaining directly into the ghost region of our own grid. So we start off our iteration by launching these asynchronous RMAs. Then we can go ahead and do some computation to overlap with that communication. As before, we do the computation for the interior cells, the ones that don't depend on the ghost cells. And then we can go ahead and proceed to wait on each operation to complete, and then do the update for our ed cells. And again, what we're doing here is we're maximizing the overlap between two communication operations as well as the interior computation to hide the latency of the ghost cell access. With this version of the code, we're launching our asynchronous operation at the beginning of our iteration, and then we do the wait for it and the dependent computation at the end of our iteration. There's actually a better way to express this dependency, which is to use a callback to attach the computation directly to the result of the arget. So let's take a look at how to do that. The member function that we provide is then on a future, which attaches a callback to it, and it gets invoked after the future is ready. The arguments to the callback are whatever values that are contained inside the future. For this example over here, where we're attaching a callback to the result of a vector arget, we don't actually produce any values from this asynchronous operation, and so therefore the callback doesn't take any arguments. Now the body of the callback here actually does the resulting computation. And through the vector arget, we're actually getting the ghost cell directly stored inside of our local grid, and so then we can go ahead and access it out of our local grid as part of our callback. As another example, here we've done the scalar version of arget, which does actually produce a value, so it produces a future double. We attach a callback to that using then, and now it takes that double as an argument. And so in this case over here, we directly use the argument as the value that was obtained. In either case, then itself is asynchronous, right? It's attaching a callback to be executed after the future that arget returns is ready. And so therefore the dot then is also an asynchronous operation, and what we get back out of it is another future. In both of these cases over here, the callback doesn't return a value, so we get an empty future that just represents the completion of that callback operation. So this is an example of just chaining a single callback onto a single feature, but we could actually do this repeatedly to construct a chain of callbacks. And so this allows us to represent long chains of dependent operations. So if we take a look at an abstract example over here, we're starting with an arget of an int from some potentially remote destination. So we get back a future int because this is a scalar arget. And then we can attach a callback to that. In this case over here, we're taking the int value as an argument, and then we're computing the log of it, which gives back a double value, so we get back a future of double. We can take that and attach another feature on it, and in this case what we're doing is we're attaching a callback that does a put to some potentially remote destination. Since we're attaching this callback to a future double, the callback needs to take a double as argument, and then we're using the scalar rput to actually move that over to some target global pointer. A couple of things to note here. The first thing is that our capture list is not empty as it was in earlier cases, and that's because we're actually capturing this local variable, the global pointer double target, in our callback here. So then we get a copy of that inside of this lambda function, then we can use it as part of our rput. The other thing to note is that rput itself returns an empty future, and then we are returning that from the callback. So normally, if we return something from a callback, we get a future of that. But in this case, since what we're returning is a future, we do not get a future of a future back. It gets collapsed into a single future. And so we just get a single future, non-nested here, as our result. And then finally, what we can do is we can wait on this entire chain of operations just by waiting on the last feature that we get. And what happens here is it waits for this callback to be done, but in order for that callback to be done, it first needs to wait for the previous callback to be completed. And in order for that to actually execute, it needs to wait for the initial arget to be completed. So what we get by this single future is representing the completion of this entire chain of operations. Now here we have a linear chain. We can also build a more complex DAG using a conjoining operation, which we refer to as win-all. And what this does is it takes multiple futures, or actually non-future values as well, and combines them into a single future that encompasses all their results. And so we can use this to specify multiple dependencies for a single callback. So in this example over here, we have two source pointers, which we're going to obtain their values using arget. One is an int type and the other is a double type, so we get back a future int and a future double from our two arget operations respectively. By using win-all, we actually get a single future that encompasses the results of both of these futures. And if we look at the types here, we see that the first argument here has type future int, the second argument has type future double, and so then our result has type future of both int and double. We can then attach a callback to that result, and now this callback has both of those argets as part of its dependencies. And so here we're doing the same thing that we did before. We're actually doing an rput over to some target destination. Only this time we're actually putting the product of our two values as opposed to just a single value directly. And as before, this rput over here returns an empty future. And since we're returning a future from the callback, that gets collapsed into a single, in this case, empty future. And as before, we can wait on that to wait on this entire DAG of operations. Okay, so what we see with .then and win-all, we have these two abstractions for constructing a directed acyclic graph of dependencies. And then after constructing that entire graph, we can potentially wait on the entire graph to be complete just with a single call to wait. Let's look at an example of doing that in our Jacobi GoCell exchange. Now there's only two asynchronous operations, but we can still, rather than having two individual waits, we can combine them together into a single future, here by using win-all. And here we're using rput actually rather than arget. And so what we get back is two empty futures as a result of these two rputs. And then win-all, combining them together, gives us another empty future. Now again, we're not combining values here, but we are combining the completion of these two operations. So this combined future will only become ready when both of these individual operations have completed. So then we can go ahead and do our interior computation and then just do a single wait call to ensure that our outgoing puts have completed. Now before we proceed to do our edge computation, we have our neighbors are sending puts at us, and we need to make sure that they have completed. And so they do so by doing a wait. And then if we do a barrier afterwards, then we know that everyone has proceeded past the wait, and so all the puts have completed, and we can go ahead and do our edge computation. This isn't the only way that we can provide the necessary synchronization. One of the things we'll talk about later is that we can actually attach a remote callback to an rput to get a remote notification that something has arrived. But that's something that we'll see later. So what we've seen so far with the RMA version of Jacobi is we've seen that we know how to allocate our grids in the shared segment. And once we have global pointers to our neighbors' grids, we know how to do the exchange and overlap it with the interior computation in each step. The last piece that we need to understand is how to actually exchange those global pointers to begin with. And so the best way to do that is using something called a distributed object. So this is an object that's partitioned over a set of processes. By default, it's partitioned over the world team, which contains all the processes. A team is a subset of processors, and the world team contains all of them to begin with. We can also define distributed objects over smaller subsets of processes. Now, constructing a distributed object is a collective operation, but it doesn't actually do any synchronization. The fact that it's collective allows all the processes to share a universal name for that object, where the name is shared, but each process has its own local value. So if we take a look at this example on the bottom right, here we're constructing a dist object with element type int, and we're constructing it over the default world theme, so over all the processes. And in this case, what we're using as the initial value is just a random number on each processor. So then what we end up with is this distributed object where each process has its own local object corresponding to the full distributed object. And since the element type of dist object was int, each of these individual objects on each process is an int. A distributed object is similar to a coarray, but it has several advantages. The first is that it can be built with a scalable metadata representation, and that's because it doesn't actually require a symmetric heap. Another advantage is that there's no communication necessary to set up or tear it down. Constructing a dist object is a purely local operation, and the same goes for destructing it. And the other advantage over coarrays is that we can actually construct this over subset teams as well. Before we look at how to use distributed object to share the grid pointers inside the Jacobi example, let's take a look at a simpler example, that of a Monte Carlo computation of pi. The idea is that you randomly throw darts inside of the unit square and see how many of those land inside of the quadrant of the unit circle. And that ratio geometrically is pi over 4. So by doing this many times, we can get an estimation of the value of pi. This computation is embarrassingly parallel, so we can easily parallelize it across multiple processes. And what we need to do is essentially just add up the number of points for each process that landed inside of the unit circle. So that operation is actually just a reduction. A distributed object isn't necessarily the best match for doing a reduction. In fact, UP++ has reductions. So if you're actually writing this, that's what I would recommend you use. But we'll use a distributed object just to get an idea of how it works and what context we can actually use it. So we'll assume that we have a hit function that throws a random dart and tells us whether it landed inside the unit circle. It'll return 1 if it does and 0 if it doesn't. And so then the count of the number of darts that land inside the unit circle is just the sum over all calls to this hit function. So what we can do is we can have a counter for each process represented through a distributed object, and that counter is an int type. A reminder that this distributed object has a local representative on each process, and so we're initially setting that local representative to 0. And then what we can do on each process is go ahead and execute our trials independently and just increment the counter, the local counter, based on how many of those give us something that lands inside the unit circle. So the way we obtain the local representative of a distributed object is to dereference it. So I mentioned earlier that we don't support dereference with star on a global pointer because that would hide communication. But here, star just gives us the local representative, so there's no communication at all involved. Once all the processes have completed all their trials, then we can have process 0 obtain the counter for each of the processes, and that involves some communication. And there's actually a fetch member function on a distributed object that does that. You give it the rank of the process whose value you want, and as with any communication, it's an asynchronous operation, so we get back, in this case, a future of int because the underlying data type is int. And then if we wait on it, that gives us the actual value of the underlying future, and then we can add that to our total. Now we need a barrier between the trials happening and process 0 actually proceeding to obtain this data, just to make sure that all the trials are complete. And then we can go ahead and do our geometric computation to obtain our estimate of pi. In this implementation, we have explicit synchronization to separate the trials from the actual fetch of the counters. However, if we actually modify this implementation slightly, we can actually avoid that synchronization and take advantage of implicit synchronization that's provided by dist object. And the way that implicit synchronization is provided is that if we do a fetch operation to a target process, and that process has not yet constructed its representative of that dist object, then that fetch operation actually gets deferred until the construction happens. And what this means is that we don't necessarily need explicit synchronization. In fact, if we ensure that the distributed object isn't constructed on a process until that process has completed its trials, then any fetch targeted at that process is not going to return until all those trials are completed. So instead what we do is we just use a regular local variable as our running total, and we increment that each time there's a hit. And then we create our local representative of the distributed object. Again, at this point, all the trials are complete, so any incoming fetch will obtain the right value. And now we don't need explicit synchronization between the trials happening and then rank 0 going on and fetching each of the pieces. If rank 0 happens to try to fetch from process I before process I is done, that fetch will be deferred until the dist object is created on process I, in which case we'll get the right value as our result. Okay, so this demonstrates that the creation of a dist object and the fetch actually provides some implicit synchronization, and it does this without a symmetric heap, and it does this without needing any sort of communication upon the creation. Let's proceed to use distributed object to bootstrap the communication inside of our Jacobi example. And so what we mean by that is setting it up so that the processes have pointers to their neighbors' grids. We'd actually like you to do this as an example. What we have in the code that we've given to you is we've done the allocation of the grids on each process. We've also done the grid pointer exchange with the left neighbor of each process using just straight RPC. We'd like you to implement the bootstrapping of the right-hand neighbor, so obtaining the grid pointers corresponding to the right neighbor of each process. And essentially what you should do is construct a distributed object, have each process put its local representative, meaning the global pointers corresponding to its own grids, inside of that distributed object, and then have each process do a fetch to obtain the global pointers of the right neighbor. So we'll break for a few minutes to give you time to work on this, and also for a live Q&A. And then we'll come back and look at the solution after the break.